towards about automaton because I want to get to the recursive part, right? So one issue with the automaton is that as we discussed before, it can explode. So if we have associativity and commutativity, which basically happens whenever you have any language, so you can have a really large automaton. And then if we also want to extract a DAG instead of a tree, and even if we just want to extract a tree, the cost of the extraction is proportional to the size of the tree. And it can be even polynomial or exponential in the size of the tree if we go to the route of the fixed ILP, or if we do answer set programming. So it's really important that we want to maybe after growing the tree, want to make it smaller to speed up extraction. So if we think about automaton and then think about wanting to make it smaller, there's a word called automaton minimization that was really well studied. It's maybe part of the intro to theory class about how to take a DFA and then minimize it, right? And then so similar things are also well studied for tree automata. And then we actually try out the idea to say, can we take a tree automaton and then minimize it so that we can make extraction faster, and it works pretty well, right? So to some extent, so one small improvement is that even if we minimize the automaton, if the exponential number of permutation of say multiplication is still not merged, so we still have a really large automaton, and then there's really no reason to explicitly represent all the permutations. So what we are looking at right now is that can we do some notion of automaton minimization modulo these equivalences to further shrink the size of the automaton. So that's one of the research projects which we're working on right now at Simons. Yes?
Does that take the cost function into account, or is it just symbolically?
Yeah, so let's see. Let's say no, yeah. So the extraction part takes care of the cost function.
So with this method, do you recover kind of classic optimization technique like hoisting stuff out of the loop and stuff like that? So
right.
You do something more a little formal, like for this class of optimization, equality saturation can be covered.
Yeah. So so there are maybe two theoretical results, which is that if we have a set of railroads that's complete, which means that it's able to prove any true identities, then in theory, given infinite time and space, we can discover any optimization that's identity. And then a little bit more practical is that if your proof size is less than n, then equality saturation will discover that program within n iterations. And then the hope is that the graph doesn't explode within n iterations. So sometimes it does. So that's also a real challenge. Okay, so now let's switch gears into recursive programs. And then, so this is stuff I learned while working with Mahmoud, Heng, Reinhard, and Dan. So thanks to them for teaching me the work. And then this is mostly work done by Esparza's group. So I think Esparza will also visit this program in the future. But it's helpful to rinse and repeat just to make sure people understand. Okay, so another goal for this program is that at the end of the program, everyone will be able to write data log. So I'm gonna introduce the data log syntax one more time. And here is the conjunctive query we see, right? This is a non-recursive data log. And then we just say that in the first rule, it says that the tuple XYZ is in R if we have XY in E and then T and YZ in T. Right, so this is how to read one single data rule. And then we can also project things away, and then that just means that you compute the same R, and then you throw away the Y attribute and then make it into a set by deduplicating. So the example down here is that given that we have inputs T and E, which are both this table, which is visualized by this graph, then the R relation we're going to get what we're going to get is going to be 1, 2, 3, 2, 3, 4, and 3, 4, 5. And then S relation, we just project away the Y column to get 1, 3, 2, 4, and 3, 5. Okay, and then to make it recursive, we basically just put an atom in the body atom in the head as well. So here we have the world's simplest recursive data program. So in the base case, we say that everything that's in the edge relation, we say that is in the transit closure of the graph. And in the recursive case, says that if we have an edge between x and y and z are in the transit closure, then we also put x and z in the transit closure. So here we're just computing transit closure of the graph. Right. The way we do it, the way we evaluate this program is that we start by assigning all of the recursive relations to empty. So here T0 starts as empty. And then if a relation doesn't appear in the head, we say it's an input relation. So E is just a relation that's constant, that's always this. Right. And then at every iteration, we'll fire every single rule and then add a result into the head relation. So in the first iteration, we fire the first rule, and then we see that T0 was empty, so we add everything from E into T0. And then the second rule says that we join E with T and add a result because T0 was empty. There's nothing to join. So this rule produces nothing in the first iteration. Right, so in the first iteration, we just add the E relation as is into the T relation. In the second iteration, it gets a little more interesting. So we look at the first rule. It still says that move everything from E into T. So we already did that. It doesn't change anymore. And then the second rule now fires because T1 is now non-empty. So we will join E with T1 and then add a result back into T itself. So this is the same join we saw on the last slide. So we just add these three tuples, 1, 3, 2, 4, 3, 5 into T. And then by the end of the second iteration, the T relation contains all of these tuples. And at this point, the third iteration doesn't add anything new, so we converge and stop. Okay, so now we're gonna twist our understanding of this picture a little bit into linear algebra because everything is linear algebra. So there's internet meme about that. So one important concept is active domain of the database. So these are simply all of the values that we see in the table. So here we have 1, 2, 3, 4, 5. And then, so once we have the active domain, we can have this kind of bit vector encoding of any relation using the active domain. So we simply just take the Cartesian product of our active domain. So we have 1, 1, 1, 2, 1, 3, 1, 4, and then we have one entry for places where there is a tuple, right? So here's a 1, 2 tuple in the iteration. So we have 1 over here for 1, 2, and then there's no 1, 3. So we have 0 over here. There was also no 1, 1. We'll have 0 over there. And then we do this for basically all possible positions that we can get from the active domain. And then in this way, we can essentially represent the iteration as this big vector. Right. And then the length of the big vector will be 25. So does this make sense for everybody? Okay. So now we represent it like this. And we can essentially think of our data program now as applying a function f onto this big vector, which represents the state of the T relation at each step until a fixed point. So now the function f is a function that maps a 25-dimension big vector into a new 25-dimension big vector. Right. And then we can generalize this a little more. Right. So we were working with the submarine of Booleans before, and we generate this to work over the submarine of reals, or submarine of tropical numbers. We can encode more interesting programs, maybe like a matrix multiplication, and then we have also shortest path programs. So we can encode it like this. And then in general, the goal of data log evaluation is to find a fixed point for the function f, right? Such that applying f one more time to the fixed point doesn't change it. Yeah, and then so one important part is that in this talk, we're dealing with a particular kind of submarine that's called a closed submarine. So satisfies all of the usual identity of the submarine of any submarine. So we have associativity of add, commutativity, zero identity, one identity, and then the special thing is the last one. So this is the one to pay attention to. So we define this closure operator that has the property such that 1 plus A times the closure of A is the same as closure of A. So think of it as a clean star, right? So if you add one, and if you multiply, the clean star by the same letter, and then you add one to it, you get back the same thing. So essentially, you can think of this star as the clean sequence where you have 1 plus A plus A times A plus A times A times A all the way at infinity.
Remy?
Yeah.
Can you help me understand why we're doing the 1 plus part?
In a future slide, yes. Yeah. And then, so this is a really nice paper. It's by Lehman in '77 that really clearly characterize these closed submarines. So going back to dialog evaluation, so our goal is to find the fixed point of some vector function f, right? And then the standard implementation is the so-called naive evaluation, also called clean iteration. And literally, we just apply f to empty, and then again, and again until we converge. Right. So this is the standard way. It's really, it's actually pretty efficient because we can really parallelize it, vectorize it, so it actually can have really efficient implementation. But actually, we're going to use math to do some magic to make it faster, and then we're going to get help from two of our old friends, Gauss and Newton. So this is also from the really beautiful paper from Lehman. And in the first paragraph, I just really like it, so I'm going to read it really quickly. And then he said the Warshaw's algorithm for computing the transit closure of a Boolean matrix floats algorithm to a minimum cost path. And clean is proof that every regular language can be defined by a regular expression, and Gauss-Jordan's method for inverting real matrices are the same thing, right? So these different algorithms from this very diverse set of disciplines actually can be unified under the same framework, and that's exactly what Lehman did in this paper. So this maybe this is a start of answering like why do we add one to the star, right? So if you look at this this Stella program, we're essentially multiplying E to itself. If we think of E as a matrix, right? So we're essentially multiplying E with itself, and then adding the result into the previous iteration, right? So in the beginning, we have just one single E, so that's where we started from, and then so that's basically the right. So we start with E, and then the second iteration computes the two paths, which is E times E, and the third iteration computes the three paths. So that's E to the third, and then. So if we do this until convergence, we can factor out 1E, and then we see that here's our sequence, right? So the identity plus E times E all the way to the finish. And then by definition of our clean star, this can be written as a closure of E. So this is all kind of informal. To formalize it, we can look into paper, and then there's actually a precise way to understand this. So now let's prove that this E star we use by abusing notation actually satisfy this property that's prescribed by the closed submarine. Okay. So we want to prove that 1 plus E times E star, remember E is a matrix, equals to E star. Right. So we just start by expanding it. E star is by definition over there. It's 1 plus C plus E times C all the way to the right. And then we can once again push this distribute this multiplication across the process. So now we get back to I plus E times C all the way to the finish, and this gets back E star as we expected.
Yeah, so Remy, you don't need any finiteness for this sequence, right? That converges or anything, or you do?
I believe not.
Okay.
Yeah.
So you don't need something to say this is well defined or something like that.
Well, yes, he does. So, Remy, you said that you're going to use math. Didn't you
Yes.
You just said that.
Yeah.
that 3-line thing, yes, that's not a proof.
This one?
Yeah.
Yeah. Let's see. Well, why is it not a proof?
Because it implies, for example, you need to know that sum is well defined. It's an infinite sum.
Mhm.
You need to know that multiplication is distributed over those infinite sums. A whole bunch of things that you need to know, and you can only prove them if you have some extra structure there. And you were going to talk about that extra structure, the ordering structure, and things like that.
Yeah. So let's talk about it during discussion. So I didn't prepare to go to that that much, but I agree
I
that's
think
important for math.
would be quite disappointed.
Okay. So I'm sorry for Gus, but let's make him happy in the afternoon. Okay. So here's right. So we want to solve for this to actually solve for this this closure without actually computing the potentially infinite sequence. We're going to we'll just use cleaning iteration to compute it. So back to the paper, the claim is that we can use the Floyd-Warshall cleaning algorithm, which was used for generating compiling regex into automaton and then finding shortest path to compute this closure expression. And here's really the really simple algorithm. And let's just specialize it into the case of regular expression to help our understanding. So we just have some arbitrary ordering of the states in the automaton, right? So we talked about automaton in the previous session. So we assign these indices to the automaton, and then this is our result. This is the matrix we're gonna store our result in, or the automaton we're gonna store our result in. So we initialize with empty, and then for every state, every pair of states from 1 to n, we are going to look at the previous automaton, and then try to find whatever states we have, and then we have an alternation that we find the states find the automaton that goes from I to k, and then k to itself and k to j, right? So we do this for every pair, and then we do this loop for every k, and this is basically lets us construct the final automaton that recognizes the regular expression. And then similarly, we can think of shortest path. So here, to find the shortest path from I to j, so we either take the previous shortest path from I to j, or we find another shortest path from I to k and k to itself. So here, in the shortest path case, this is just empty, right? With positive weights, and then k to j. So this is a really simple algorithm to solve this algebraic path problem, actually. So this takes n cubic time, and then in certain cases, okay, so an improved algorithm is actually they call it Gaussian elimination, which is a bit of a stretch, but it basically adds a little more back substitution into the algorithm. So this is a pretty good paper to read about the theory and practice. And then in certain cases, actually inspired by program analysis in programming languages, we can do this instead of cubic time, we can do this in nearly linear time, right? So this is a paper by Tarjan saying that for certain graphs that are called reducible, we can discuss more what that means. We can compute the closure operation in m basically linear time to the number of edges. And so this is a reverse Ackermann function, right? So for these reducible graphs.
Can you tell us what these graphs are?
Huh?
Can you tell us what the reduced graph means?
Yeah, so basically the reduction of a graph, you can do two things. So if there's a self loop, you delete the loop. And then if multiple, if one vertex has multiple edges kind of coming to it, but all of those edges come from the same parent, you can kind of retract that edge. So if you retract this until you cannot anymore, and you get back a single vertex, so that's called reducible.
Okay.
Yeah.
You talk about multi-graphs with set loops, right?
Yes. And then I think there's a way to generalize just to regular graphs as well. Yeah, so I have an example I need to look for that's not reducible. That we can look at in the afternoon. Yeah. Okay, so another cool thing is that we can actually compute matrix inversion with this closure operation, right? And here's the proof. I guess proof now. So first of all, we basically want to prove that the inverse of B is equal to identity. And then we start like this. So we define it like this. So we have I minus B, the closure of I minus B times B. And then we just change variable, right? We call I minus B A to get to the second line. And then we distribute to get to the third line. And then by definition, A star is 1 plus A star times A. And then we get it over there, right? So by just rearranging this equation, we get this equation to there.
Did you
Yeah.
minus operation? You are under semi-ring, right? So
Yeah, so this is the case where you have a ring. So this only works where you have, say, like real numbers. It doesn't work for semi-rings. Okay, so the takeaway here is that we can use these Floyd-Warshall shortest path algorithm or Gaussian elimination to compute the closure for linear data log program in qubit time. And that's actually pretty cool because we before this we didn't really have any runtime guarantee of recursive program in general because we don't know how long it takes to converge. But here we have this really simple algorithm that give us qubit time convergence, which is pretty nice. And sometimes we have linear time if the graph is reducible.
So,
Okay, so yeah.
So here, what is your inputs to your linear algorithm? Is it so? Can you go to the previous slide? So what tell us what's exactly the statement? So you're giving us A, which is the matrix,
Right.
and then you can do it in cubic time and in the dimension of the matrix, right?
In the size of the matrix.
The size of the matrix is n squared, right? So, but you say you're going to take time in cubic, right? So it's cubic in the dimension, right? Or
I think it's a size, but I need to check on this. Yeah.
The dense model, so it's the number of vertices of the graph for
Yeah. I see. So it is the dimension.
and cube.
I see. Okay. So yeah, dimension. Yeah. Yeah. So but this is really only restricted to linear data log program. So what this means that in the data log rule, we are only allowed to join a recursive relation with a non-recursive relation. So in our transit closure example, we joined E with T. So that's linear, that's okay, that we can handle. But if we have nonlinear programs, maybe we join a recursive R relation with a T relation, this algorithm doesn't support that. So for that, we need to go to Newton's method. And then I guess I have 10 more minutes. Yeah. Okay, so really going back to this picture, the standard way of evaluating data program is by naive iteration. So we just apply F until it stops changing. And then if we look at general kind of a numerical analysis, we know that another way to find a fixed point is by taking a linear approximation at some point, and then step using the derivative. And then the chances are this takes fewer iterations to converge than the naive iteration. So this is basically the idea of Newton's method, and then I will try to write down the keys, right? Right. Yeah. So remember, our goal is to find the fixed point, which is larger. X equals to fx. So here again, f is this vector function from R to the n to some semi-ring to the n to the semi-ring to the n. Right. And then if we rewrite this a little bit, we're really just finding the solution to this other g of x defined to be fx minus x. So we're finding the 0 for this function over here, right? And then so the Newton's method goes like this. So we start as at some x0, and then for every step we take a first order approximation of our function g. So we have this is g xt plus g prime xt times x minus x. So g minus plus 1. Right, and then over here, once again, g is a vector function, so this is basically the Jacobian of the g function. Right. And then we set x t plus 1 to be the solution of this thing. So, dx. And then if we rearrange it a little bit, we get x. Yeah, so this is the Newton's method over real numbers, which works fine. And then for us, there are a few issues we need to fix. So because we're working with semi-rings, we don't really have a notion of minus. We don't really have a notion of inverse, and we don't have a notion of derivative. So we're going to define these so that this algorithm still works for the semi-ring case. And then the way to do this is actually, so I think for the details, let's work it out in the afternoon. But really, for the derivative, we just take kind of the derivative using the algebraic rules, right? So we have the the chain rule for multiply, and then for derivative of a constant is 0. So that happens to still work if we work with semi-rings, right? And then in the general algorithm, so as at each step, we're going to compute this derivative, and then instead of taking the difference, we're going to find the delta such that x plus xt plus that delta equals to let me write it down. So for the delta, we're going to have the property of xt plus delta equals to f of xt. So we can find any delta with this property. So for example, when plus is idempotent, we can just simply use f of xt for the delta, right? And it still helps because we have fewer iterations of applying f in that case, right? So that's derivative and minus. For the inverse case, instead of just inverting the expression here, we're going to use the closure operation to compute the inverse. So that was a few slides ago. I showed you that we can compute this notion of inverse with the closure operation. And then we're not going to get exactly the inverse because, as Jiba pointed out, we're dealing with semi-rings. But when we compute the closure like that, that gives us an expression that basically satisfies this equation, right? So for all of that, there's a lot of juicy detail. I guess we have a lot to talk about in the afternoon. Yeah, and then so some other properties we need to check is that we have this definition of derivative just from the algebraic rules from calculus, and then how do we know that it works? How do we know that it actually respects the semi-ring semantics of a program? So the only thing it really needs to satisfy is this inequality. right? So we say that for any semi-ring function f, if fx plus the derivative of x times any other semi-ring z, it needs to be less than or equal to f applied to x plus z, and then we can see that holds for our definition of derivative.
So what notion of inequality do you use in an arbitrary semi-ring?
So for any semi-ring, there's a natural order, which means that a number is less than something else if that number plus something is. So let me write it out. So
Only naturally ordered semi-ring.
yeah, so for naturally ordered semi-ring, it's defined like this. Yeah.
So that is the restriction that is needed for applying Newton's methods to arbitrary semi-rings. They need to be naturally ordered.
And I believe every closed semi-ring is naturally ordered. Okay.
We just require it to be naturally ordered.
I see. Yeah. So both it needs to be both closed and naturally ordered. Yeah. Okay, so I think this is a proof, but we can do it as a homework. And then for this delta, the question is that how can we pick this delta that magically satisfies this property? And we can look into that more in the afternoon. And then as another exercise, so we can try to evaluate this nonlinear program using Newton's method, just as an example to see how it works concretely. Okay, yeah, so I think we have a few minutes for questions, if we have any.
Yeah, so I mean, just briefly, if you can, I would love to get some sort of intuition for like, what is this computing on a simple program like shortest path to reachability? Like for naive or semi-naive evaluation, I could state it very easily, like iteration-wise, like I compute all the 1 path and the 2 paths and the 3 paths, and I'm using these all together, like load and multiply, have all the paths.
Yeah.
Right. So can you do something like that for this approach?
Yeah. So this example will kind of show that, and then another way to think of it is that so we're really just when you have a nonlinear program, we're just really just fixing one of these to be constant, and then we run the program until convergence, and then we kind of alternate between them. Yeah. Yeah.
So one question I have about this method is you're somehow comparing different things, right? Because in the clean iteration, each iteration is just a computation of a fixed point.
Yeah.
Here, each iteration of your Newton method is actually a fixed point computation, right? So if you count the total number of iterations as fixed points, in the one you multiply the number of like Newton iterations times the times you need per fixed point in your Newton.
I see. Yeah. So so you're saying that the total work might be larger, and it's true.
So what I want to understand, what I think I don't understand is when does it make sense to do that, right?
Yeah.
So somehow you need to argue that the cost of your linear fixed point is actually going to be cheap enough that it's going to be worth it, right? So do you have like any thoughts about that, or?
Yeah. So one example is that when the graph is reducible, then we have linear algorithm to compute the inner fixed point, right?
Okay.
So in that case, I think there are cases where Newton is actually, if we count total work, is faster. And then another idea says that maybe the inner fixed point is easier to parallelize. So
that is true.
Yeah. Okay. So
and
yes. So in that case, we basically reduce to the work versus depth trade-off, right? So it's easier parallelizable.
Yeah, just to Paris. So we had an application in our 2014 paper on circuits for data logs. So there is a corollary of the, as far as I recall, the results that actually tells you that there are only a limited number of iterations that give you, under certain conditions, the fixed point, whichever way you obtained it. And actually for us, for certain semi-rings, that allowed us to prove that there exist circuits of a polynomial size for certain problems.
These are the absorptive semi-rings, right?
Yeah, for certain provenance semi-rings like the Boolean expressions and perhaps more interestingly something called the absorptive polynomials
Yes.
and so on. But so that's a, you wanted an application, that's an application.
But I mean, that has nothing to do with Newton, right? That the cleaning,
So
it says that the cleaning.
the Newton, it uses a corollary of the fact that you get to the fixed point after a certain number of iterations.
Of clean iterations, they're not Newton iterations.
Should be about clean iterations?
I don't think you looked at Newton's iteration in
Yeah,
that
we
paper.
looked at.
Yeah.
We used the theorem, I think. We didn't use the actual Newton iterations. Anyway,
This is a 2016 paper or
14.
okay.
Okay, let's take a 5 minutes break, thanks Remy, and then, yeah.